Okay, so today I'm going to be talking about an algorithm, a classic algorithm that in the Kleinberg and Tarta's book falls in the framework of a greedy algorithm, and this is called Dijkstra's algorithm. Dijkstra's algorithm for computing the shortest distance from some fixed initial node S to every other node V in a graph. The graph consists of G, and it consists of a set of vertices V and a set of edges E. And every edge in that graph is, first of all, directed. We're talking about a directed graph, so every edge has a direction, and every edge has a distance. Let's say this one is 3. So just to establish a notation, L of UV, that's the length of the edge from U to V. In this little example, it's equal to 3. We'll see a complete example later. But given a directed graph where every edge has a distance to it, we want to compute what is the shortest path distance from S to each one of the other nodes. Now, that's a general problem of shortest path and shortest distance. Dijkstra's algorithm works under an additional restriction that's actually very common, which is that every length, every edge distance is greater than or equal to 0. So in this particular application, the graphs of under consideration will have no edges that have negative distance. Now, you might wonder what a negative distance is, but there are definitely problems that we'll want to model that have negative distance, and we'll talk about those later. But certainly, for any kind of physical implementation, distances, real distances in space, distances, geographical distances, or distances that represent time, or even money when it comes to an expense rather than an income, then the distances on each edge are strictly greater than or equal to 0, and so this assumption is fine. And that simplifies the algorithm for shortest path, and also allows faster algorithms as well. So this is the problem under consideration. So let me define something here. Move over here. This is a definition for a node U in the graph. Du is defined as the distance of the shortest path from U to from S, that's the start node, to U. Okay. I should have said one other thing. These individual distances or lengths of edges can be infinity. If there's no edge from U directly to V, if that edge doesn't exist, then we say LUV, the length of that edge, is equal to infinity. That's just a technicality that lets us deal more uniformly with all of the edges instead of saying always, well, if the edge really exists or if the edge doesn't really exist, and so on. All right, back to here. For a node U, D of U is defined as the distance, that means the true and correct distance of the shortest path from S to U. And we'll also, in the algorithm, Dijkstra's algorithm, we're going to have a programming variable called D of U, and we'll want to prove that what the program sets for D of U is, in fact, the correct value. A little bit confusing to be using both of those, but hopefully that won't cause too much of a problem. All right. So to describe the algorithm, I'll describe it first in generalities, and then do some pseudocode. Okay. So inductively, as the algorithm proceeds, we're going to let S be the set of nodes set of nodes of all the nodes, such that the algorithm has set D of U. So it's the set of nodes U. In other words, S is going to be the set of nodes where the algorithm thinks it's already correctly computed the D of U for that node, correctly computed the distance. So initially we're going to start out with S, little s, will be contained in big S, and the algorithm is going to set D of little s equal to 0. Well, that's clearly correct. The distance from little s to itself is actually 0. Okay? So the algorithm starts out correctly, and s is contained in little s, and everybody else is outside of s. Okay? And then, for each node v that's in capital V minus s, okay, the algorithm determines what? It determines the shortest path distance, or the shortest distance of any path from little s to v, okay, from little s to v, which has the following property, that uses only nodes in capital S until it reaches v, little v. Okay? So capital S, again, it's the set of nodes where the algorithm thinks it's already computed correctly the shortest path distances. And then we're going to find, for every v that's not yet in capital S, what is the shortest path to v that only uses those nodes that are already in capital S, plus one additional edge that's going to go directly to v. Okay? So let me just draw a general picture of that, sort of a cartoon picture. Okay, which is, here's our starting point S, and at some point in the algorithm, here we have big S. Those are the set of all the nodes that the algorithm has already computed the distance for. And then we have a node here, which is in capital V minus S. And among all the paths that go through capital S and then by one edge to V, the algorithm will compute what is the shortest of those. There may be another path, for example, like that goes to V and so on. But the algorithm is going to set d prime of V equal to the minimum over U contained in S of d of U plus the length of the edge UV. So again, this is this represents the length of a particular path that goes through some node U in S, okay, and then it goes directly to V, and that edge has length UV. Okay? So this is then the path length of this particular path is du plus the length of the edge UV. All right, and we're going to take the minimum over all of those nodes U that are in S, and this is done for V contained in V minus S. So the algorithm, again, at every step has this capital S, and then at every step it computes or updates, we'll see how we can update this, d prime of V for every V that is not yet in S. And then it pick V contained in V minus S to be the node of smallest d prime v value. Okay? And when it does that, what it does is now it's going to put that v that it's just selected into capital S. So this is how capital S grows. So in this picture, what would happen is that capital S would expand. If this is the v that has the minimum d prime v value over all the nodes that are not in S, then put v into capital S, and so capital S expands out here to now contain now to contain this node little v. And additionally, in order to reconstruct the actual path, this algorithm right now is just computing numbers, but in order to reconstruct the actual shortest path from S to each of the other nodes, what we're going to do is keep this set E tilde. It's a set of edges, okay, and it's going to be augmented E tilde together, so all the edges that it has so far, together with the edge VU, where V and U are the nodes that are picked here. Now, that's a directed edge that goes from V to U, so it's backwards that way. And we'll see later why we wanted to direct that edge backwards. It'll help a lot in reconstructing the shortest path. So this is kind of a pointer which is remembering that the shortest path to V ended with an edge from U to V, but we're going to remember that backwards, from V to U. You'll see in a minute why that's necessary. Okay, so let me get another. All right. Let me actually try to. This got a little bit spread out here, the whole algorithm, and I think I have time to consolidate a little bit and write it down in a little more formally, so it's a little bit cleaner. Okay. So here it's in some sense just a repeat, but putting it all in one board. So S is initially just little s, and d of s is 0. That's how we start out. And then we say while s is not equal to the entire set V, and we're going to have E tilde as the empty set. Then we're going to select a node V that's not in capital S to minimize du plus L uv, okay, where u is in capital S. And remember that if there is no edge from u to v, then this is set to infinity. So those edges are not really going to be part of the consideration. Those pairs of nodes where there is no edge from u to v, it won't be part of the consideration. But formally what happens is because this value is infinity, this just never gets included in this minimization, or it never gets chosen. Okay, so that's you select V, and then you add V to capital S and add VU to E tilde, okay, and that's the end of the while statement, okay, and yeah, so that's it. That's Dijkstra's algorithm in one board, okay, and I'll give you a little example, and then we'll see more particularly what this E tilde is doing here, okay? So let me give it a small example. Okay. So let's have this graph. There's a little s there, and then an edge to a node A, and an edge to a node B, edge to a node C. It goes directly there. One to E, one to F. Okay, and D. Here, 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 here. Okay, and oh, one more there. Did I miss any? Well, how would you know? I mean, I have the one. I have the example. 1, 4, 2, 3, 3, 2, 1, 3, 1, 8, 1. And this little example is similar. It's almost identical to one that's in the book, in the Kleinberg-Tardish book. But I've modified it a little bit for purposes of illustrating some things. And let's say that we're at a point in the algorithm where what's in S is little s, A, and B. So capital S at this point consists of little s, A, and B. Okay? So like that. That's what's in capital S at the moment. Make this little s littler, all right? So there's no confusion. Yeah, there's a Superman S right there. Okay, now let's look at what the d prime values are at this point. Well, first of all, the d values, d of s is 0, and d of a is equal to 1, and d of b is equal to 2. So implicitly, I'm assuming here that the algorithm, in fact, does correctly set its programming variable to the actual shortest path distance. And in a minute, we'll give a formal proof of correctness of the algorithm where that will be an explicit assumption. But in looking at this example, let's also assume that the algorithm has correctly computed d of a equal to 1 and d of b equal to 2. Obviously, it correctly computes d of s equals 0. That's not in doubt. All right, but then what are the d prime values? So these are the ones in S, and d prime of little d, let's look at that. So since d prime of, well, the only way that we can get to little d through a node that's in capital S right now is through A, and d of A is 1, and then with this additional edge, d prime of d is equal to 4, and d prime of c. Well, to get to c, we could get there either directly from little s, because that's in capital S, that would be a 4, or we get there through a, that would be a 2, or we could get there through b, and that would be a 5. But the important thing to note here, when I say, okay, this could be a 5, I'm not looking at the whole path. I'm just using this formula here, this what's written here, to say, well, the distance to b, right, that we already have computed is 2, and then we add the 3 that makes it 5. I'm not looking at the whole path, even though in this case it's so simple that it's not much different than looking at the whole path. But to get the idea right, to get the algorithm right in general, we want to think of what I'm computing here is the known distance d of b plus then that additional distance along that edge, not the distance along the whole path. Even though it happens to be that, I'm not looking at that whole path. All right, I think I've beaten that to death. So this is the min of 2, 4, and 5, which is equal to 2. Okay, let me write this equal to 2. And then d prime of e equals 6, right? E is 6. Oh, it's actually 5. Okay, because to get to here, we have, the only way of doing that is 2. It was d of b plus 3, which is 5. Okay. 5. All right, and d prime of f, just to be formally correct, is infinity. Okay? Because there is no way of getting to F through a path that just uses the nodes inside capital S and then one additional edge. At the moment, d prime of F is equal to infinity. All right. So working the algorithm, what's the next step of the algorithm? The next step is that it looks through the d prime values and finds what the minimum is. So we have a 4, a 2, and a 5, and obviously the 2 is the minimum. So V in the algorithm is in this case C. Okay? And so then what the algorithm does, it puts C into capital S. So capital S expands like this. A bit messy, but capital S expands to be there. All right? A, B, and C. Like that. And D of C is now set to be equal to what this value is. So D of C is now set to be equal to 2. And we can remove this because C is no longer in S. Oh, did somebody leave their phone on? Okay, hold on a second. Hello, I'm in the classroom. Oh, yes, hi, I'm sorry. I'm teaching a class at the moment. Could I'll have to call you back later. Okay, I'm sorry. All right. Yeah, bye. Sorry about that. Okay, let's get back to this example. Where was I? A little break in the work here. Okay, so we were just removing C because C has now been put into capital S. All right. Now, what I didn't do is I didn't update these the E tilde, and E tilde is, let's just mark those edges like that. That's an edge that had been put into E tilde. That's an edge that had been put into E tilde, right? And then now, with this step, this edge is now into E tilde. And the thing that you can see is that if you start from C, that's the new edge, that's the new node that was just put into capital S, then if you follow the edges of E tilde, you'll get back to little s. And that, in fact, shows you the shortest path from C to S if you would reverse the directions, which means it's also the shortest path from S to C if you go backwards. So why do we write these pointers backwards instead of forwards? Because I want to be able to ask later, what is the shortest path from S to some particular node that's out there? And if I had the pointers going forwards, I wouldn't know that I was actually moving towards that node as a shortest path. But the pointers that I do establish, E tilde, have the property that from any node, there's only one pointer out of it. So if I want to know what's the shortest path from S to some particular node way out there, V, well, once we're done, I'll have a pointer from V backwards, and that'll have a pointer backwards, and that'll have a pointer backwards, and that'll eventually come to S. And that path, I've just scoped out that path without any kind of breadth first search or any kind of searching there. It was just follow a pointer, follow a pointer, follow a pointer, all forced. And that'll tell me what the path is. It tells me it in reverse order, but then I can reverse that particular order and say what's the shortest path from S to V, and I have that in my hands. Okay, so that explains a little bit about E tilde. Maybe I should take this one step further. Now that C has been placed in capital S, we can update the D prime values. D prime of D, what is that now? It's the minimum. D prime of D becomes the minimum of what it was previously, which is 4, or one new possibility, new candidate, is the distance to C plus the length of the path from C to D. Okay? And in this case, the distance to C is 2. The distance from C to D along that one edge is 3. Okay, so that becomes a 3. And the shortest, the smallest between 4 and 3 is 3, so that gets changed there. And D prime gets updated. Now, that isn't to say that D gets put into capital S yet. It's just the D prime value changed. Why? Because capital S changed. Let's see if anything else changes. D prime of E, previously it had been, D prime of E had been 5. Now we have the possibility of 2 plus 2, which is 4. So that changes also to 4. Okay? And then D prime of F had been infinity. But now you can get from C, which has a D value of 2, plus 8, that makes it 10. Okay, so that changes. And then over all of the nodes that are not in capital S yet, we find the one with the smallest D prime value, which is 3. And so S expands now to contain D, and the E tilde now contains that edge as well. Just eyeballing where this is going, 2 plus 2 is 4, that would be 5. So this is going to be an E tilde, and then this is going to be, okay, so if I took the additional 2 steps, which I didn't do in detail, the edges that I now have squiggled are the edges in E tilde. And one thing that's you should note is that the edges of E tilde form a tree that's rooted at little s. And that is clear that it's a tree because for every node that's in the graph, there's exactly one node, one edge that touches it that's in E tilde. Okay? So this is the edges that are in E tilde form a tree, and that's sometimes called a shortest path tree, or sometimes called a Dijkstra tree. Okay. So that's the algorithm in an example. Now I have 2 things that we need to do. One is show that it's correct. I really haven't shown it's correct. Secondly, look at an implementation and talk about its running time. Okay, so let's say correctness. So claim when the algorithm sets D of V for node V, in other words, when it puts V in capital S, okay, D prime of V is the correct shortest path distance from little s to V. Because at the moment that the algorithm puts little v in capital S, make this a smaller v to be sure, it sets the programming variable dv to be equal to d prime v. And now we want to prove that, in fact, when it did that, that d prime v was, in fact, the correct shortest path distance from little s to v. Maybe to make that a littler s. Okay. From little s to v. All right, so we want to prove this. And the proof is going to be by induction. Proof by induction on the size of the set capital S. So initially, when size of capital S is equal to 1, then the only thing we have, only little s is contained in capital S, and d little s equals 0 is correct. That is, I apologize for this ambiguity. D of S is both a programming variable and it's defined to be the actual correct shortest distance. And now we're trying to prove that when you think of this as a programming variable, its value is in fact equal to the correct shortest distance. Well, here, when you interpret this as the programming variable, the algorithm sets D of S to 0. And when you interpret this as the correct distance from S to itself, it's 0. And the two are the same. So the basis is certainly true, or the algorithm certainly has done the right thing for little s. Okay? So now we'll assume that it's done the correct thing when capital S is of size k. All right? So assume the algorithm is correct up to the size of S equal k, or less than or equal to k. Up to, anyway, up to the first k times that it puts an element in capital S. And now consider the k plus first entry into capital S. Okay. All right, so we're going to suppose, what's the node that gets put into this point is just noted as V. That's the node put into capital S. So what do we know about it? We know that V is the node that minimizes du plus LUV, and that's for U contained in capital S. Okay? So that's what the algorithm picked. It picked the node V that minimizes this over all the nodes that are not in capital S. Okay. And we want to prove that, we know that this is D prime V. We want to prove that D prime V is in fact the shortest distance of any of the paths to V. Okay? Well, let's just consider what another path to V looks like. All right? Let's take this over here. Oh. Whew. All right. So our situation at the moment is this is capital S. Here's V, which the algorithm has decided to take into capital S. And here's the node U. That's the last node on the path that the algorithm is looking at. The last node in capital S that goes to V on that path. Now let's look at some other path that's different than this. Okay, it initially has some nodes in capital S because it starts at a node that's in capital S, and ultimately it goes to a node that's not in capital S. So there has to be some first node, call it Y, which is not in capital S. So this is a path P. So let P be any path from little s to V, and let Y be the first node on P not in capital S, and let X be the node before Y on P. Okay, so this is x right here. This is x, this is y, and this is an alternative path, and so from y it goes by some path to v. Okay, so we're essentially trying to prove that this is the shortest path to v. V is the node that the algorithm picked, and so we know something about d prime v. And we're also trying to prove that d prime v is the correct distance to this node. And here is some alternative path. Okay? And that alternative path has to start at little s, and so it initially uses some nodes that are in capital S. But then it has some last node that is in capital S, and then a first node that's not in capital S. All right, so now consider the algorithm at the moment when it picked v to be in capital S. Well, y was a contender. Y was a node that's not in capital S. Okay, y is not in capital S. So it could have possibly been picked to be the next node to be in capital S. It was a candidate. It was considered in comparison to v. But what happened at that point was that d prime v was less than or equal to d prime s, d prime y. Okay? Because the algorithm picked v. We know that v was the smallest over all of the, it has the smallest d prime value over all of the nodes that are not in S. Okay, now it's possible there's a tie. Okay, that's why I allow the possibility of equality here. But you certainly couldn't have the other direction. All right, well that's the path length from S through X, which we assumed inductively this distance is correct. Okay, this is the true shortest path length to X. Oh, yes? Oh, that's a very good question. Very good question. Yes, d prime x is the shortest path length to X. How do I know it's equal to the length of this path to X? I don't. A very good question. But what I do know is that this path length here cannot be any less than dx, because that would violate the definition of dx. And inductively, the algorithm has correctly computed dx at this point. So the length of this is at least dx. Okay? And I could consider what is actually the shortest path from S to X as another alternative way of getting. But the point is that, therefore, the length of P is greater than or equal to dx plus Lxy. And again, I don't know that the first part here is exactly equal to dx, but it's got to be greater than or equal to dx because it is a path from S to X. Okay? So length of P is greater than or equal to dx plus Lxy plus whatever the length of this piece is. Okay? So I'll call that maybe P prime, and this is the length of P prime, LP prime. Okay, so let me just, okay, let P blah, blah, blah. Hopefully everybody remembers what P is. So what do we have here? This, dx plus Lxy, that's d prime of y. Okay, that's defined as d prime of y. And what is LP prime? What do we know about LP prime? Well, the only thing we know about it is that it's greater than or equal to 0. It can't be negative because there are no negative weight edges in this graph. And by the way, this is the first time we've ever used that assumption. I said that initially that Dijkstra's algorithm, in Dijkstra's algorithm we assume that there are no negative weight edges, but we never used that assumption up until this point. And it's a critical distinction. I mentioned that Dijkstra's algorithm is faster than general algorithms for shortest paths, so we better use it somewhere. So hopefully those of you who'd noticed that we never used that assumption yet, we're getting a little anxious. And here's where we use that. This is always greater than or equal to 0. And so this is greater than or equal to d prime x. Okay? D prime y, sorry. D prime y. Okay? So we knew by algorithm d prime v is less than or equal to d prime y, and now we've made this argument that says that the length of the path p, this alternative path from s to v, alternative path that we're calling p, we have d prime v is less than or equal to d prime y is less than or equal to the length of that path, and therefore d prime v is less than or equal to the length of that path, which means that this particular path, which has a length of d prime v, is in fact shorter than any alternative path from s to v, and therefore d prime v is the correct shortest path distance from little s to v, which means Dijkstra's algorithm is correct. Again, the assumption that there are no negative weight edges was critical here at this point in the proof. And if, in fact, there were negative weight edges, this point in the proof would break down because this part, L of P prime, could have been negative, which would then not have allowed these implications to go through. You can also, by simple example, cook up a graph where it has negative weight edges, and in fact, Dijkstra's algorithm fails to find the shortest path distances. Okay, so we've got correctness now. What's the running time? Well, okay, let's think again about what the algorithm is doing at each step. Whenever a node is placed into capital S, the d prime values of all the remaining nodes, the nodes that are not in capital S, have to be updated. Okay, so in fact, we've got this here. We say when a node, let's call it U, is placed in capital S, and we have to do an updating for every V that's not yet in capital S. We set d prime V equal to the min of whatever it was. Okay, so maybe it won't change, or it'll be d of U plus L uv. We're using the possibility that because we just put U into capital S, now there's a new way of getting to little v through the nodes in S, namely we'll use the node U as the last node in capital S before we get to v. So we have to make this comparison to see if d prime v is going to be updated. Now think of this updating over the entire algorithm. How many times do you update the edge, or how many times does d prime v get updated? I don't mean it gets changed necessarily, but we have to look to see if it gets changed, gets updated due to a node U going into S. Well, only once. Over the entire execution of the algorithm, that only happens once, which means that we only have to look at an edge, UV, in part of this updating once over the entire algorithm, which means that the entire number of updates that we have to do over the entire algorithm is order of the number of edges. In fact, it's less than or equal to the number of edges. So over all of this, so over all the algorithm, these updates cost something's proportional to the number of edges in the entire graph. Okay? That's that update. Now, we also have to pick, at every step, we have to pick the node V, and remember this little thing here is equal to d prime V, we have to pick the node V that has the minimum d prime V. We were just talking about updating d prime values. How do we pick the node that has the minimum of all the d prime values? Okay. Well, of course, we could just scan through all of those nodes, all of the nodes that are not in capital S, and look at what their current d prime value is. But that's less efficient, and I'll let you figure out what that time would be if you did it explicitly, like that, looking through all of the nodes. But that's less efficient than keeping a priority queue. A priority queue like a min heap. So I'm assuming you know this, or you can look it up. Maybe you've learned this in a previous data structures class. So a min heap allows you to put in values. It allows you to extract out the minimum of a value, and allows you to update values, each of those in log n time, where n is the size of the heap. Okay, updates extract min and insert values. Each of those can be done in log n time. And so what we're doing when we want to find the node V that has minimum d prime V, that's picking out the min. When we're putting in a value, a new entry that has a, well, we could start out with all the d prime values equal to infinity, in which case there really is no insert. But when we update a d prime value, because of what we did over there, then the updating could be done in log n time. Now, the point is, what is n here? N is just equal to the order of the size, the number of nodes, because we're going to keep in the heap one value for each one of the nodes, at most. And then it decreases as the size of S gets bigger. What's in the heap gets smaller. If we started out with all the nodes in the heap equal to the infinity. And so each of these operations takes log n time. So Dijkstra's algorithm can be implemented in order E times V, E times log V log V time. And that's it for the time analysis, and this is relatively efficient. E is generally, the number of edges is generally small compared to the number that it could be. There could be as many as n squared or V squared, but generally not. Graphs are typically sparse, and then log of V is a fairly small multiplier. Okay, so a fairly efficient algorithm. Now, that's it for the technical part of the lecture. I just want to add one historical note. In 1981, I was teaching and taught shortest paths. And you have to remember, in 1981, most of you weren't born by then, but the IBM PC, which was the first real PC, had not even really come out yet. And that had 6 meg, I think, or 4 or 6 meg of memory. Meg. I mean, that today is not enough memory to hold a good photograph that you take on your digital camera, that you take on your phone. Okay, those are 7, 8 megapixels, whatever. That's really small. You all know that. And bigger machines, the machines that might have, I don't know, 100 meg or whatever, were big, physically huge machines. And I had a student in 1981 who came to me and he said he wanted to learn more about shortest path algorithms because he had this idea that someday, and in fact he wanted it to be fairly soon because he wanted to make a lot of money from it, someday people would be able to have in their cars a computer where they could enter in where they were going. And in it would be enough maps, and it could do the computations using Dijkstra's algorithm, something like that, to tell them what was the shortest path they should drive. Now, there was no really good I/O at that point. There weren't good monitors. I don't know how he thought he was going to do the I/O, the input-output. As I said, computers were huge that had the memory to be able to have maps in them. The maps are representing what? The entire United States? Or I mean, I knew this guy was nuts. Okay, this was never going to happen because I know that we knew that computers were the sizes of houses or rooms or baseball fields or whatever. But of course, today, everybody carries around. Well, this phone actually doesn't have GPS on it, but you all know what a GPS is, and I do actually have a GPS that's about the size of that, which does everything that he was talking about and more, because it has the satellite GPS as connecting to it as well, which he didn't even anticipate. But just to say, these things, we taught this sort of as a theoretical thing. It's obviously a very practical algorithm on a real computer, but the idea that it could be used by everybody in their cars every day was just out of the question, and yet, here it is. All right, thank you. See you next time.